Ja, ich will zwischendurch eigentlich nicht wieder
Okay, so now switching to neurocognitive methods and programming. So today is the last session, also in this course. Could you please close the door? In terms of slides, essentially, because the second part of this course, as I announced previously, is magnetic resonance imaging. So we want to understand a little more about the magnetic resonance imaging. Or if you're not interested in that, you can also do the EEG course, as we also previously discussed. So from next time on, I have to think how it is. So in this course, from next time on, we start with magnetic resonance imaging, meaning that we first discuss differential equations and then again look into the quantitative aspects of magnetic resonance imaging, so the Bloch equations and so on, and then discuss Fourier-based imaging, now that we know all about Fourier analysis, so that we really know how MRI works. That's in this course. In the other course, where we just finished Fourier analysis, we will start with GLM analysis of fMRI data, which you can also think basically starts after this session in this course. So we will talk about GLM analysis of fMRI data, and we will use these 2 sessions before Christmas, which I originally hadn't dedicated to that, to multiple linear regression. Because the GLM analysis of fMRI data is multiple linear regression. And to at least give you a little bit general GLM theory, I thought it would be helpful if we at least spend these 2 hours on that. I've been asking you to watch the GLM stuff previously. You should really try to familiarize yourself with matrix multiplication and multivariate Gaussians. So we will go over this quickly in these 2 hours before Christmas, but not in the depth that I have previously done that, for example, in these videos, and also not in the depth as it's in the script. So please look at matrix multiplication if you're not happy with that in the script that is on my website, and also look into multivariate Gaussian distributions. So that you are somewhat happy with that. In the application to multiple linear regression, we will discuss that in a little bit of detail in the next 2 coming weeks. Yeah? So that's the plan, so that today we finish our intuitive introduction to the whole fMRI business, and after that it's essentially fMRI data analysis, and the first fMRI data analysis that we will do is GLM until the end of the winter semester. And then the second fMRI analysis that we will do is DCM in the summer term. And if you want also at one point hear about multivariate analysis of fMRI data, you're welcome in the academic year 1920, where I will teach multivariate again after some time that I haven't taught. Yeah, so that's the general layout. It's a little complicated, but if you just come here and you will learn useful stuff. You can also view it as that. So today, fMRI data preprocessing, which is, at least in some labs, a big thing. In papers, it's usually like 3 or 4 sentences that say we did realignment, smoothing, and normalization using SPM 12. And that's usually what this refers to. And to get started, it is helpful again to remind yourself and everyone of how fMRI data are organized, so that you know where pre-processing actually starts. So this is something that we've seen before. So you have your participants, they come for sessions, you acquire data in runs. In a single run you have a time series of EPI volumes. Each volume consists of a number of slices. Each slice consists of a number of voxels. Based on acquiring data in a single run, you get time series of the MR signal over voxels. Yeah? So this is how the data is saved. So you have a time series for each voxel. So you have a spatial domain there, and you have a temporal domain. Yeah? So this is what you should always keep in mind when data analysis starts. Usually how the data are organized are actually files per time point, so that you have a file that holds the data for all voxels for a given time point, and then if you have acquired, let's say, 150 time points, you have 150 files. There are also what is called 4D files now, which are a little bit more compact, so that you have the 3D spatial data times the 1D temporal data in one file. This is where things start, voxel time courses. And this is a plot from the book by, I think it's Paul Drake Nichols and Mumford, on fMRI data analysis, which is nice as an introduction. The book on the pre-processing. So the typical pipeline in terms of fMRI data analysis works as follows. So you start with the reconstructed image data. Reconstructed image data means that you have done the inverse discrete Fourier transform of the data that was acquired in K-space. So you start with the images, and then you can do a number of steps before you start with the statistical analysis or the actual data analysis. And things that one can do are, for example, distortion correction, motion correction. Distortion correction is not always done. This is why there's this direct link to motion correction. Then you can do slice timing correction. However, this is also not always done. Then you can do spatial smoothing. Normally there is some spatial normalization step also in here, which is not shown. What this is mainly trying to indicate is that there's a number of pre-processing or processing steps between the data that you get from the scanner and the data that you then apply, for example, your classifier to, your GLM to, your DCM to, or your own model that you developed yourself because you're a real scientist and not just a toolbox using clicking monkey. And monkeys are nice, nothing against monkeys, but this is sometimes in labs kind of how things are. So you should aim for actually developing your own models and not use the models that other people have proposed. But if you want to do that, you should also, of course, know what other people have proposed and understand the models that other people have proposed. So, based on these two things, starting with that, this is the outline for today. So there's some quality assurance, distortion correction, slice time correction, realignment, smoothing, and anatomical normalizations. What are these things? What can we say about it? That's what we're going to do. Quality assurance. What can be done to make sure that the scanner is actually doing what it's supposed to do is to measure MR phantoms. And then to look at these and detect common artifacts. And common artifacts, so this is something that you should know, are things like spikes or ghosting and strong signal inhomogeneities. So if you basically become a scanner operator by doing this course with Christian Kainz, whom you all know because you attended the safety seminar, these are things that you actually learn to see, and I will show you examples as well. And this is important as a first data quality screening test, because if you try to do statistical analysis of data that is corrupted, no one has any benefit from it. So there are some common MR artifacts, spikes, ghosting, signal drop, and inhomogeneities that you should be able to detect visually. So what are MRI phantoms? MRI phantoms are essentially, so in the simplest case, they are just bottles of water that you can put into the scanner, into the head coil, and then scan and look at. So here, for example, is a phantom that is just some saline water-filled ball. And if you make an image of that and you find that the image is completely distorted, so you don't see a ball in the image from the scanner, but something different, then of course something is wrong. There are more advanced phantoms. This is here kind of a pseudo-brain phantom. I don't think we have something like that at the CCNB. These phantoms are a little bit more around, so they have some geometric shapes that you can image and then check whether these geometric shapes are also fine. So typical thing is what MR physicists or radiographers do to do scanner maintenance is that once a week they scan such a phantom and then look at the images, check whether, for example, the raw signal to noise ratio is good, and check for their geometry. So these are MRI phantoms. You should also, when you become a scan operator, learn how to scan a phantom and look at it, so that you know what that is, an MR phantom. So now going to detecting spikes in MR images or different kind of artifacts. So this is an image which is fine, except that I don't know why they chose this image, that there's quite a big tumor here, which is actually quite sad for the participant, but somehow I think it's from the MR handbook, they use this image to demonstrate what a spike is. So this is a kind of normal image. A spike basically looks like this wave-like pattern in the data, so that you have these stripes. This is called spikes. This usually signals, this usually doesn't occur in all images, in all slices, but occasionally occurs and is in general signals some malfunction of the hardware and is one of the times where you would call the vendor of your machine to check out what is going wrong, because as Christian Kainz also discussed, this is not something that we then deal with ourselves, but then the Siemens people have to come if there are spikes and check what the problem is. So the point here is not so much to understand where this pattern comes from, but to know that a spike refers to this stripe-like pattern, and it means that there's something wrong with the scanner. Call Siemens or Philips. Ghosting is another artifact that sometimes occur. This actually has to do with aliasing in terms of the image reconstruction and the frequency stuff that we discussed last hour. It's called ghosting because you have here the image of the brain at the top of the head, roughly, not quite, but going towards the top, an EPI image, and you see that there is kind of a wraparound of data points here, so it gets a little bit, if you emphasize the image, you see that here again, and you have the front of the brain here. So these artifacts are called ghosting. You can, the theory there is, one can actually understand if one goes a little bit into the Fourier and discrete Fourier transforms and the questions of aliasing. So this is where these things come from. Usually, however, is not so much that something is going wrong with the Fourier transform, but what is going wrong is with the signal acquisition itself, and then there are two, then the real and imaginary components of the raw data are wrong, and then you get these kind of things. It's not what we discuss in detail here, it's just another artifact that you're supposed to be able to see. So ghosting, and I've heard the terms. MR signal inhomogeneity means that towards the center of the image, the data is much brighter than towards the edge of the image, which is also an artifact and not given by the sample itself. Yeah, it used to be a bigger problem. It's especially a problem for things like cortex and white matter dissociation, what's that called, segmenting. So if you try to create a mesh of the cortical surface, then you need an image processing algorithm that distinguishes cortical voxels, so dark gray voxels, from light gray voxels. And if you have this strong inhomogeneity, especially at the edge, that's quite hard for an algorithm to do. So if you have these inhomogeneities, then there's a problem. So you should see if this is the case, but this is already going more into a problem that the radiographers or the MR physicists seeing many more images than you should detect. And finally, signal dropout. So you know that, or you might not know, but then I'm telling you now, that you have dropout specifically around air-filled cavities of the head. So the sinuses, for example, so the sinuses, which are these air-filled cavities in your bones, not the sinuses that drain the veins. And around these, for example, in the temporal pole or the orbital frontal cortex, you just don't get much MR signal. And specifically here for EPI, the dropout is much stronger than here for the T1 image. So here you have quite some signal dropout. So signal dropout just means you don't record a signal. Yeah. So these four artifacts, spikes, ghosting, inhomogeneities, and signal dropout, you should be able to detect on images. You should see them, and essentially what it means for you is if you see spikes and ghosting, talk to the radiographer and or your thesis advisors and say the scanner is not working correctly. Inhomogeneities, hopefully you won't have them. If you have them, talk to radiographer and advisor. Signal dropout, it's natural for things like orbital frontal and temporal pole. If you're particularly interested in these areas, you need some special sequences which try to avoid strong signal dropout there. Otherwise, you just have to deal with it and say, okay, that's fMRI. We have this signal dropout. And of course, looking at these raw images is a first thing in data analysis and of course quality assurance, because if you have a lot of spikes in your data and you don't look at the raw images and then analyze your data, it will be funky and nobody knows why, and it's weird. So look at it. Yeah, that's quality assurance. Next, distortion correction. So distortion correction in the context of fMRI means the following. If you image an object, for example, such a phantom, which is here a ball, and the image of it looks like that. So you see that there are some distortions in the sense that this doesn't look like a ball. Then you have a distortion, which can be, for example, caused by non-homogeneous magnetic fields or gradients that don't produce uniform and linear gradients. In this case, it's actually due to the field. What you can do is acquire an image of the magnetic field, so essentially measure the inhomogeneities of the static magnetic field, and then use this information of essentially the distortion of the magnetic field to interpolate and recalculate the MR image here. So you basically know, okay, the distortion is in the magnetic field, so I can use this information to do better here and get a corrected image. This of course doesn't work only for phantoms, but it also works for EPI data. So here it's an example for distortion that is actually resulting from an interaction between, what's this? Let me think. I'm not quite sure whether this was actually, that might be an artifact due to some metal implant here. Not quite sure whether this is, don't think this is standard frontal signal dropout. The main thing is that this was the API images that was acquired. At the same time, there was a field map acquired in magnitude and phase, because this is acquired in Fourier space, as we will learn in January. And this information can then be used to unwarp, this is how people call that, or correct the API image. And you see that it's mainly doing something here. Distortion correction sounds awesome. There are tools also to do that. It's like always when you try to correct data that was somehow not acquired correctly in the first place. This is then, in a sense, artificial data that you generate, and it works not, so it does something, but you will still be faced with the fact that your raw data actually had signal drop out there. So one can try it, and in some cases it might make a difference and help for something, but it's not like it's the most standard thing that people always do. There's also actually the way that SPM, for example, does that is that it also tries to correct for distortions in the motion correction step, because it tries to also measure inhomogeneities there. So distortion correction does exist. If you ever want to do that in your data analysis, you will look for toolboxes. You will come across Chloe Hutton, who has established a lot of this at the Phil. It's not the most common thing. That's distortion correction. Yeah, question?
Yeah, I don't know if I missed it, but on your slide, there's this difference image. What is that?
Yep, I think I didn't really explain that. So that's the difference between the unwarped or the corrected API images and the original API image. And you should see that the difference is mainly here and a little bit here. It's just, it's just a nice image from or a nice figure from this MRI analysis handbook by Paul Druck and colleagues. Good, so quality assurance, distortion correction done. Next, slice time correction. So what does that refer to? So as you might recall, and as we will also discuss again, MRI volumes, so 3D images, are not acquired in a standard setting all at once. That would be 3D imaging, or as people also call it, one-shot imaging, which happens, but so one can do it, but it's still not the most common thing. I don't know, do you, from your fMRI papers, I know you're not reading fMRI papers, you're somehow reading all sorts of papers, but not papers that actually have to do with fMRI or EEG. But does anyone in their fMRI paper came across 3D imaging / one-shot imaging or slice time correction? We came across slice time correction. Okay. Slice time correction was there, good. So if there was slice time correction, that meant people acquired the data in slices, so they did 2D imaging, because most people do 2D imaging. What that means is that you acquire the data slice by slice, which is, yeah, good. This seems to be reinterpolated, because you can see that for each slice you have kind of 3 voxels here, but of course this is something that actually happens. So if you, for example, acquire slices of thickness 3.5 millimeter, you often in SPM reinterpolate this to 2 by 2 by 2 millimeters, so that you have a little bit more or a little more voxels per slice thickness than you had originally. Thing is, these slices are not acquired exactly at the same time, and depending on how they are exactly acquired, they might actually be quite different, even if they are close together in space. So this shows, first of all, that slices are acquired not at the same time, and it's an example for an interleaved slice acquisition scheme, which first at time point 0 acquires this slice 1, then at time point 0.25, so 250 milliseconds, slice 3, 500 milliseconds, slice 5, 750 milliseconds, slice 7, and then it starts again here and does the remaining slices. The reason why interleaved slice acquisition is sometimes done is because in terms of the excitation, you try to be specific and you want to avoid kind of a spillover of excitation between this slice and this slice. So if you would do it immediately here, this would be a little bit pre-excited and maybe then already in terms of signal decay, decayed more. So instead of exciting the second or the spatial slice directly adjacent to your first slice, you leave something out. However, that's also not completely true. A lot of acquisition schemes actually are not interleaved. So you can also just do descending and ascending slice acquisition if your focus for a given slice is actually quite good. So depends on your signal acquisition.
So this difference in time for each slice is not due to, it's not on purpose, but because you excite different slices continuously.
Well, not continuously, discretely. Yeah. So it's in this sense, it's on. So the thing is that, and we will discuss that in more detail in January, is that usually you do 2D Fourier imaging. So you identify a slice based on. So you remember that this is the Z direction. So that you identify a slice based on its lambda frequency. So you have a linear gradient in the Z direction, and then you have different lambda frequencies across the Z direction. So from here to here, then by sending an excitation signal specific to the lambda, to a specific lambda frequency, you excite a different region along the Z direction. And then the in-slice temporal or spatial imaging is done by a Fourier transform. That's 2D Fourier transform imaging, which we'll discuss in detail more. But this is the common way, so that you have a slice-based acquisition. Yeah?
Are there devices which excite different slices at the same time? Are there devices which excite different slices at the same time?
Yeah, so that's what I meant by one-shot imaging. So essentially, so in a way, it's not completely different because then you have just a thicker slice. So then you can also excite the whole thing and then do 3D Fourier transform imaging to get the spatial information out of it. But the common thing is that you do slice-wise acquisition. Yeah. So that maybe also to bring that back. So that's also what this means, that the volumes, they actually partition into slices because you have, for each volume, you have, let's say, 30 or so slices. There was another question.
Yes, are the data points on one slice, so that would be the X and Y axis? Yes. Are they all acquired simultaneously?
Almost. Almost. This is actually, this is then case-based imaging. So essentially how that works, which we will discuss in January, is that there's then a link between how long you have the gradient on and which frequency you acquire. So it's all done in frequency space. So for a very long time, you acquire the high frequencies. So you do a Fourier space frequency acquisition. So the frequencies are not acquired at the same time, but the image points that you then get from reconstructing the frequencies, so doing the inverse Fourier transform, they are kind of from the same time because they are on average from the whole thing. So they are not acquired one box by one, but they are acquired in frequency space. And there we have to discuss more to really see that. Yeah? But in principle, they are acquired at the same time, which means throughout the whole period.
How do we determine how many slices do we want, and like what implications?
Yeah, so this essentially depends on how much you want to image. So here the idea is that you do full brain imaging. So you acquire slices that cover the entire brain. That means if you acquire this much in space, so if your field of view in 3D is like this, that has certain constrictions on how fast you can do that. But you can also say, okay, I'm only interested in visual cortex because I'm a vision scientist and I go to VSS and I do deep neural networks and correlate them with V1 to V5 and my brain ends here. And then you just do Fourier slices. So that depends on your application. So, but what I actually want to talk about here is that these slices are acquired or can be acquired at quite different time points, which then leads to a sampling of the bold response at quite different time points, and that's shown here. So here the idea is question or
no, I was just thinking this. I actually wanted to ask something. I'm sorry, it might be a stupid question, but when you acquire these slices, who said that we acquire them along the z-axis? That's why I did this.
Yeah.
Just to think. So could we also? I was thinking like if it is also possible to.
Yeah, it's also possible to not do the non-Fourier imaging, so the excitation-based signal encoding or calling in, for example, the y along the y-axis or the z or the x-axis. So that depends on how you actually do the gradient. So one doesn't have to do it according to the z-axis. But again, this is something we go a little bit more into detail once we do actually the imaging. Should not forget that we haven't really talked about the imaging yet. Because this needs Fourier analysis and these needs differential equations. And we have now the Fourier analysis. Now, in terms of these different time points when slices are acquired, what this leads to, especially, for example, if you do an interleaved acquisition, this leads to quite different, or can have effects on the sampling of the bold response. So this is the example. You have a brain area here. Now the idea is that slice 15 is measured, then slice 17 is measured, and then slice 16 is measured. Yeah. Here you have a typo in the Hütte, because it should go slice 15, 16, and then 17, and not 16 again. And then the story goes as follows. In this area here, you of course, or here, you have a homogeneous bold response, which is this black thing. Yeah? So it goes up and it goes down again, like the bold signal does. And now you acquire this thing in an interleaved manner. So first 15 and then 17. So the 15 is blue and the 17, that is wrong, is red. Because they are quite close together in time, you acquire them here and here. Now, a long time after that, because this basically relates to the image before. So you see that here you have 0 and 25, and then the one in between is only acquired 1 second later. A long time afterwards, you acquire the slice in between. Of course, in this time, the bold response has increased. And you now have the following for slice 15 and 17, you have roughly the same value, and for slice 16 you have a larger value, although it's especially essentially at the same location, but this relates to the fact that the time that you allocate to this slice is always the TR value and not the specific slice value. Yeah? And this then, of course, holds if you do this again. So the slice 15 and slice 17 always have kind of the same values. Slice 16, which is in between, has different values because it's in time, it's always later than slice 15 and slice 17. Yeah? No? Yes?
No, I just don't understand. I thought it's the slices are applied in chronological order.
Yes, but
we would start with 15 and then 16, 17. I don't get why 16, which is in between, is the latest one.
Yeah, so there are two things. One thing is that this refers to an interleaved sequence like shown before, so that you actually do this, and then 2, 4, 6, 8. So it refers to an interleaved sequence. So if you're not using an interleaved sequence, then it's not that strong, definitely. The other problem is that you always treat the data from one volume as one time point. Yeah? So although the data are effectively acquired at for a given point in space, or at least a given slice or a given point in Z space, at different time points, if you analyze the data or look at them, you treat all data from one volume as acquired during one TR. Yeah? So you say that all my voxel data here are acquired at time at 1 second. These are at 2 seconds. These are at 3 seconds. In fact, some slices were acquired at 1.5 seconds, and some slices were acquired at 1.8. So, and this is how this slice timing effects come in there. And I will, one can do something by it. This is what is called slice time correction. So this image is not really that helpful. It just shows that you can interpolate. So for example, if you have, I'm not even quite sure how to interpret that. This shows just some interpolation of data one can do. The thing is, with the whole thing with slice time correction, there are two things to say about slice time correction. First of all, if you have short TRs, the difference are not much. So if you have a TR of like 1 to 1.5 seconds, the differences that you actually have in terms of the bold signal are not much, because the bold signal is not changing that much within 1 second. It changes, but it doesn't. It changes more on a time scale of 4 seconds. The other thing is that slice time correction, so doing something against these differences, works best if it doesn't have to do much. So if the slice timing effects are minimal, then it works. If you have big differences, then interpolation, of course, gives you interpolation error. So slice time correction makes sense or works well if you don't need it, and it doesn't really work well if you need it a lot. These days, it's not that needed anymore, because TRs are not in the range of like 3 seconds or so, but more on the 1.5 or something like that. Finally, the whole problem just comes in because you don't do your analysis based in a slice-specific manner, but in a GLM-specific manner. So ideally what you would do is to do a GLM analysis with onsets that are temporarily done in a slice-specific manner and not done in a volume-specific manner. I said that every year since 6 years or so on, and every year I say, please develop a GLM that is doing a slice time-wise GLM, and nobody ever does it. Because everybody studies then clinical aspects of, I don't know what. So this is the story about slice time correction. You can read blogs of that online, so I never do slice time correction because it's not really worth it. Yeah, but the problem is kind of understandable. You can do interpolation against it, but then interpolation will maybe not really work. Of course, I'm also not explaining in detail here how this interpolation really works, because I would have to talk about interpolation. So yeah, you can do slice time correction. You cannot do it. Better would be to do slice-specific data analysis. Please develop that. That's slice time correction. How are we doing for time? Let's start with realignment. Maybe let's just do one session. I think we can do this whole thing in one session. or you don't feel like you need a break, right? It's not like we have J indices and omega J's and going from -1/2 to n+1 or something. It's pictures and some talk that one can listen to or not. So realignment then. Realignment, also known as motion correction, is something that is actually always done and is also sensible to do. So head motion is of course an issue because the scanner, when it images things, it assumes that the sample stays in the same position during the imaging process. Of course, if you have your brain in there, you do a couple of images over time, and then you move your head somewhere where in the data grid that the scanner puts a certain sample, the data will be completely different if you move your head out of this data grid. Of course, this is not what participants usually do. However, there's a little bit of movement even if you try to keep your head still. And especially at the edges of the brain, this actually makes big differences. So here you see the gray level values when things are like that. And then if you do a little bit of movement here in this direction, then you see that the data changes quite dramatically. So it goes from 119 here to 520. So motion affects the values that you get for your voxels. That's what this slide wants to say. The effect of head motion, which you then sometimes pick up using your regressors that pick up variance because they are themselves a variable. You can usually see that the head motion was not fully corrected by getting activations or voxel significances at the edge of the brain, because this is where the motion effects are most pronounced, as the previous slide had shown. So what can you do? The best thing about the whole thing is, of course, preventing head motion. Preventing head motion in the first place. So usually you put the participant into some cushions. What you can also, in this way I looked closer, use these, and I think this is actually one, use these vacuum-based cushions that where you can suck the air out once people are in there, and then they are kind of in the mold that is specific to the head, and then they really feel if they move. They are not the most comfortable ones, and especially if you have your head for a long time on a quite hard surface, it starts to hurt, because you compress the capillaries in your skin, and it actually gets quite uncomfortable at one point. You can use bite bars, but that's also not really done, and you can go to your favorite SM studio and be strapped onto a table and then look like that. Sorry. I just find this image funny. Nobody does this kind of thing, but this image is awesome. Yeah, every year the same joke. But at least it's on video now, so I don't have to make this joke here. So essentially you try to tell your participant that they shouldn't move, and why is he's even naked as it looks, right? So he doesn't it doesn't seem to wear anything. That's completely weird. Anyway, that's the prevention of head motion. So that's the most important thing. So tell your participant to not move their head, and also try, if you're a participant yourself, not to move your head. There is still residual motion, which you might be able to get this in, especially if you're dealing with kids. What one can do, and this is what's shown here, is using mock setups, specifically with specific participant groups like kids, to train them to stay still. One can also do that. Usually the common participants are, of course, your fellow scan students, so also we don't have a mock scanner here. You will not train them, but to encourage them to stay still. Even if they stay still, there's some residual motion also, for example, by the heartbeat, which pumps blood into the head, of course, and there's a little bit of movement also associated with that. So one needs to correct for that. And what is typically done in terms of correcting for head motion is that 6 parameters are estimated, namely parameters relating to translation in the X, Y, and Z direction. So if you move your head up, to the left, to the right, or back and forward. And so that would be 3 parameters, so X, Y, and Z translational movement, and rotation around the X, Y, and Z axis. So these are parameters, 6 parameters that are typically estimated. What of course doesn't play a role for head movement correction is the scaling. So the head of course doesn't get bigger or smaller by movement or any kind of sharing things. These kind of operations and estimation of their parameters, they are important for normalization that we will see later. So for correction of head movement, usually 3 translation parameters, Z, Y, and Z, Z, Y, X, Y, and Z, sorry, and rotation, 3 rotation parameters, X, Y, and Z are estimated. This shows then basically the logic of how this is done. So you have here the original time series in volumes, so these are not slices now, these are volumes. This is one slice of a given volume, and for each difference between 2 volumes, 6 parameters are estimated that relate to the translation and the rotation, and then these parameters are used and are applied to the original image sequence to reslice, that's the term there, to reslice or interpolate the raw image to obtain a movement or motion corrected volume. So how that then looks in more an applied setting is as follows. So if you run a realignment algorithm, what you have to specify is a reference image, and then the realignment algorithm estimates the translation and the rotation with respect to the reference image, which is usually just your first image. So you say this is my reference, and then the algorithm tries to estimate the translational and rotational parameters, and then you get, for example, if you do an SPM analysis in the end for here 3000 volumes, you get the parameters. So you see, for example, that there was quite some movement in the z-axis, and then here there was some jump in the z-axis where maybe the participant did something. However, this is not really much, this is in millimeters. Same for the rotation. The rotations around the x, y, and the x, y, and z axis, they have names. They're called pitch, yaw, and roll. You don't have to remember which one is which, because I don't remember which one is which. But yeah, so they these are the estimated parameters. These parameters then are applied during the reslicing, and this shows what the result is, for example, for translation. So before motion correction, so before essentially reslicing the images, these were the parameters. Then after motion correction, if you again try to estimate the parameters in terms of translation, they are much lower. So that means that the algorithm is at least self-coherent. So first it estimates this movement, then you reslice so that this movement shouldn't be there anymore, and then afterwards it doesn't measure that much movement anymore. And this is, I think, just the relative displacement, I think, between slices or so. Don't quite remember. The important thing is here that the translation is first strong, parameters are estimated parameters are used for reslicing or interpreting the raw data, and then afterwards it's better. Yeah, So that's motion correction.
I have a question. You said that the algorithm tries to estimate the parameters from one first image, so is that
No,
a static image or?
No, so what it cannot do it based on one image. So it does. It's always so. You take the first image, and then the algorithm estimates how much the second image has changed if you assume a translation and a rotation, and what the parameters of this translation and rotation are. Yeah, so it tries to basically match two images. So it, let's say this is the original image, and then your next image is that. What the algorithm tries to do is try to use rotation and translation. So let's say it's like this. It tries to do a translation and a rotation so that they are aligned. And if, of course, you need, this is of course a technical algorithm, so you need some kind of loss function, and you try to get to this where you have minimal loss, and then you can try different translations and rotations to achieve that. Once you have achieved that, you of course know for the second one how you got there, and these are then the parameters. Yeah. And then you do it for the next slice, again with respect to the first one.
Okay, yeah. Yeah, but the parameters, I get them from the algorithm, but the algorithm needs the parameters, right?
So there you have to, this is, I mean, this is a little bit more going into the actual data analysis, but there are two steps. So one, this is why in SPM, for example, it's called estimate and reslice. So the algorithm, there are two algorithms. One algorithm estimates the parameters, and then you have the parameters and you can look at them, but the data is not corrected. And then there is an interpolation algorithm or an interpolation step where these parameters are used to resample the original data. Yeah. So the first algorithm doesn't need the parameters because it estimates them. The second algorithm, which is just an interpolation, needs the parameters, but it doesn't estimate them. Yeah? Estimate and reslice. Good. This shows that it works. And my favorite topic, smoothing. Maybe to come back, so the first thing that makes sense in terms of data preprocessing from my perspective is definitely quality assurance, to look at the raw images and then do realignment, because then you have, you do some motion correction, you get rid of some motion artifacts, and you have motion corrected your data. Often what is also used in kind of pre-processing, I think I usually do that after normalization, but it's here now before normalization, is spatial smoothing, which is just computing essentially weighted averages with then in this context called kernel function, which is just a Gaussian, which is then usually quantified in terms of its full width at half maximum, which is just a conversion of its standard deviation. So if you have a large standard deviation, you have a large full width at half maximum. So half maximum means that you are at the 1/2 between 0 and its maximum, and the question is what's the full width here. So that's the conversion formula between standard deviation and the full width half maximum, but this is how things are quantified for Gaussian spatial filters. Of course, the data we are dealing with is actually not one-dimensional, but two-dimensional if you do it slice-wise, but you actually do it volume-wise, so it's three-dimensional. So you need to, you basically use 2D Gaussians or 3D Gaussians, and you see the isocontours here. This is kind of the task to familiarize you a little bit with multivariate Gaussians, so look into that. There's a whole chapter in the PMFN on multivariate Gaussians. They are just extensions of the univariate thing to more than one dimension. If you apply these filters, so these basically you put a Gaussian here, compute the average and weighted average, and then you shift the filter window and compute an average. Then what you can do with that is that you make the data smoother. So if you increase, and what this shows is if you increase the width of the filter, then for broader filter width, the data gets smoother. Yeah? So this is not smooth, this is a little bit smoother, 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 very smooth. Yeah. We discussed, I think, at one point here also this matched filter theorem. So the one reason why one wants to do smoothing is if one assumes that the activations in the brain actually look a little bit like what you see here. So these kind of subblobs in this, then of course this is not the right representation. You see that better here. That's one way how you can justify smoothing. You can also say well, this looks a little bit salt and pepper style. Nobody will believe me that here really something activated. Let's smooth it. Yeah, now it looks nice. And then there's the story about random field theory and smoothing. The random field theory based p-values, just a second, the random field theory based p-values, they actually need a measure of smoothness. So they are the p-values that you assign to peaks depend on the smoothness of the data, which is estimated from the data, and have been shown in some Worsley publications from the 90s to do specifically good if there's a given smoothness. The whole random field theory business and p-values, that's a whole semester issue that we did last summer term. So there are videos online, there's a paper online. We will not go into the details there because that's a whole new mathematical framework. But you will sometimes find that people argue for smoothing in the context of random field theory based p-values. It's not quite correct, but sometimes it comes up. That was a question.
So this filter, I don't really get it. Isn't this full width half maximum always the same for a certain distribution? Because you're just aligning two. Maybe I didn't get it at all. But also
no, so that's a free parameter of your filter. So you should not think about these things here as distributions. They are just functions. For some reasons, and for good mathematical reasons, these functions are the Gaussian probability density functions, but they are not acting here as probability distributions. So they are not distributions. They are just kind of the kernels of the filter. So you weight the data that you have by these numbers, and then you can, of course, increase or decrease the full width half maximum, because this is a parameter of your filtering algorithm. And if you increase the full width half maximum, you get a broader filter kernel, and the result of applying this broader filter kernel to the data then looks that the result of the smoothing looks smoother.
I don't get it. I don't know, maybe.
So I think the reason is that you not quite know how filters work, and that you also not quite get what I mean when I say a weighted average. So let's do an example on the blackboard. So how this works is that you have a correlation. So how this works is that you have discrete data. How do we do it? So this is your data. Like this, and then you create in 1D here, then you create a filter that then is also, of course, discrete. And you apply this filter essentially for all data points. So you compute the weighted average. So what you get out is you multiply, so you do piecewise multiplication of these things. And then at this location you sum all over them. Yeah? So you essentially do a dot product. Now if your filter is like this, essentially not much will happen, because this is multiplied with this is essentially large, and this is multiplied by this, and you allocate the average here, so it doesn't really have an influence. If you use a broad full width half maximum, so your filter looks something like this, then the data that you will put here has quite a contribution from this, so it gets smoother. So this has an influence of what you will plot here. Now, this is the first thing, and then you shift the filter window here and do the same thing. That's how filtering works.
Okay, so you apply a filter for every data point.
No, you shift the filter.
Okay, yeah. Okay, but for every data point.
Yeah.
Okay.
And that's just filtering. And then if you do this with a broader filter window, of course you will take more data from adjacent sites into the data point that you then allocate to a given site. And if you take, so you have a running average, and the running average just takes data from more sites. But this is filter theory.
So this width which you take is a kind of like a standard deviation of a certain kind of Gaussian.
It's just the width of the filter. It's just a parameter, and the standard deviation of the Gaussian you can convert based on this little formula there, this ln whatever. You can just convert into the full width of half maximum. If you want to prove for that, that's actually in the paper on random field theory.
Is it possible, for example, if you do, for example, apply the smoothing, and you can make your data not valid anymore, like if it's too much? I don't know, it's like with the sound when...
Yeah, so the thing is, there is... no. So all of this data preprocessing that we discussed here is things that you can do to data, and this is all data analysis, and there is essentially no wrong or right. What this is actually, this thing here is an example where this is from the Hütte, where it's discussed that of course it has an influence of what your results are. So for example, here the story is that if you smooth with a full width half maximum larger than 7 millimeter, then you only get activation here of one part of the striatum. Here, if you smooth with smaller than 6 millimeter, you get activity in both parts of the striatum and also some insular activity or whatever that is here. Thing is, this is all social convention. So you should smooth with, if you want to smooth data, and everybody smoothes data, you should smooth like your fellow colleagues smooth. Then everybody will say, that makes a lot of sense. And if you smooth completely different, then they will say, why? And then you need to argue why you did it differently. But this applies essentially to all of these pre-processing steps. This is all social convention. There is no right or wrong.
So, for example, here it just shows like the activation here is more strong, yes. Like you're comparing.
Yeah, but of course you never.
If we lose this part, it doesn't like make any.
Yeah, I mean, so if you have the means to really, this is of course done from fMRI data. If you have the means to really compare this with some ground truth. So if you would assume, let's say, that you have simulated, that you have built a biological brain that you can fully control, and you can induce some neural activity, and the neurovascular coupling, everything is really built in biological tissue, and you have full control of it. And then you do the imaging, and you control that you do some activity only here, and with this smoothing you get this, and with this smoothing you get that. Then you could say, okay, this smoothing is right, because you know what the ground truth is. The problem is that, of course, no one knows what the ground truth is, and it's also not, you cannot easily create it, because you would really have to build a biological brain that you have full control over. As long as this is not done, you don't know what's right. You can, of course, relate this, and this is of course the story here, maybe relate this to some other findings. So if there's converging evidence that for the contrast that was done here, only this brain region lights up. And this was shown in 100 studies, and you believe these studies really, really, really strongly. And then you find on this smoothing that the whole brain lights up. Then you can say, okay, this must be an artifact. I believe this more.
I have a question regarding the function, the Gaussian function, because you previously said that it's not acting as a probability distribution, but just a function. And I've read that you do smoothing in order to enhance your signal-to-noise ratio, and that, well, that's what I've read.
Yeah.
I just wanted to check if that's true, like that you do that to enhance the signal-to-noise ratio, and that they assume that the noise is kind of randomly distributed, so like over the brain, but the signal is not. Like if you want to measure activation, the signal, of course, is not random. So, well, what I was thinking is that this is kind of a distribution to kind of apply a kernel to equal out all the noise.
Yes, but here is just a weighting function, and if you're talking about spatial noise, then you of course would need to you can talk about spatial noise, and you can also define spatial covariance matrices if you do spatial Gaussian noise. However, in the filter business, it has nothing to do with probability. And it has nothing to do with so when you say this is, of course, yeah, it averages out noise, but you don't have a real noise model. So if what you are saying should make sense from a probabilistic perspective, then you would have to define what your spatial noise is in terms of a probability distribution, and you would have to fit that based on the data. This is not what this is all about. This is just about, there is some data, it looks like this. You do a spatial weighting by using a Gaussian filter window, and then the data gets smoother. So the problem is, yeah.
Blurring the data? Is it blurring the data?
It's blurring the data. It's like you put a blurring or a Gaussian filter on in Photoshop. That's the same thing. There's no relationship to probability theory, and if you say it minimizes the noise, this implies that, for example, you have a model in your head that says that a little voxel here that is on its own active, this must be noise. But this then must be derived based on some probability model, which wherever you read that was not the case, and is most of the time not the case. Yeah. Okay. So if you want, so the maybe going on there. So the spatial model, there is actually a spatial model that also models spatial noise, and this is random field theory, which is a spatial model, and the model of the noise is that it has a specific, namely Gaussian process, and then a statistical random field a covariance function. But this is a whole, like I said, there's a whole semester course to go into that, and we first need to talk about GLM anyway. Yeah? Good. So here, just see it as a smoothing. Smoothing just makes data smooth. That's what it does. So then to finish the whole thing, that's fine. Anatomical normalization. What this refers to is getting the brain of a single participant into some common space, so that you can compare the activations of different participants and maybe even do a group analysis where you have a voxel that refers to the same brain area in different participants. And anatomical normalization is always done when you do group analysis, and I think the common form of data analysis, if you're not doing, for example, what was this thing? Cortex layer. If you don't do layer-specific imaging, like we talked about the other day, you do some form of group imaging. And to this end, it's first important to recall that the brain has certain axes, namely a z-axis, top to bottom, a right-left axis, which is usually x, and a front to back, which is the y-axis. And a helpful thing to establish a common space for brains is that one has some landmarks that somehow define certain things. Now, this actually shows already how essentially all common brain spaces are defined. The 0 point in a brain space is always the anterior commissure, and the XY plane is arranged in the plane of the line connecting the anterior commissure and the posterior commissure. So the anterior and posterior commissure are just fiber bundles that collect the left and the right hemisphere, like the corpus callosum, but one can see them quite easily in the brain and also on T1 images. So this is something that one needs to recall, that there are brain axes and there are anterior and posterior commissure. And based on that, one can then talk about different aspects of the brain and different orientations. So this view of the brain is called a coronal view. Here you can see the X and Y axis and the superior and inferior. You have axial representations, anterior, posterior, left and right, and the sagittal view where you see the superior and the posterior and the anterior. So these are just the axes of the brain as they are defined. Now, the problem is, even if you have these axes defined, if you want to do a group analysis, you still have the case that, of course, people are of different sizes and of different shapes, and this, of course, also applies to their brains. So if you want to, on one single image, represent the activity of an entire group of participants, you need to make sure that each point in this image that represents the entire group of participants somehow represents each individual participant in a nice way, or in a meaningful way. And this essentially means that you somehow want to do away with this inter-individual brain morphology differences if you're doing group analysis. And for anatomical normalization, there are essentially two. There's one space that is usually used, which is called the Talairach space, which not more into the Talairach space and MNI term is. There are two things around, namely Talairach space and MNI space, but they are closely related, and this is what I'm trying to explain now. So Talairach space is a normalized brain space, and this is its history. So originally, Talairach space was proposed by this guy called Jean Talairach in 1967, I think at the MNI. And it essentially uses a Cartesian space, so just a common X, Y, and Z coordinate system, and a 3D proportional grid in this in this Cartesian space. And the Talairach space is based on a set of anatomical landmarks, namely an anterior commissure, posterior commissure, the midline sagittal plane, so that's in between your hemispheres, and then the exterior boundaries of the brain at each edge. And its origin, and this is important also for MNI coordinates, is that it's there where the anterior commissure, as I've shown on this other slide, intersects the sagittal plane. So how does it look? This is what it means. So Talairach space is defined as follows. So here you have the anterior commissure and the posterior commissure. This is the origin of the Talairach space. So this is the 0, 0, 0 point. And then Talairach space extends until the borders of the brain, and that's essentially it. And its midline axis is defined by this interhemispheric cleft. No? So essentially you can think of putting just a rectangular box or cuboid or whatever you want to call it around the brain. And this is if you have an individual brain, it's completely defined by its origin and the edges of the brain. Now, why was that done, and why is that interesting? Because there's also something called the Telaera Atlas, which is a brain anatomy atlas, which does something like Simon Eickhoff implemented in the SPM anatomy toolbox, essentially without implementing it. So it is an atlas that describes the names of brain areas based on a single brain, and it has labels for brain areas in the sagittal, coronal, and axial sections. And this Telaera Atlas is based, where is it? Yeah, this is based on, of course, a single brain. So you have to think how this works. So you want to make an atlas of the brain. Okay, somebody has died. You take the brain, you cut it into sections, and then you label the areas based, for example, on histology, like we saw last week. And then, for example, you say this is Brodmann area this is Brodmann area this, and that, and so on. Now the problem is this is based on a single participant. And this single participant, of course, might have a different brain shape than people that you are currently investigating. Now, if you then want to figure out a label for a brain area in the participant that you're currently investigating, you somehow need to map your participant data brain to the brain that was used in this Telaera atlas. And for this, Telaera proposed a simple procedure to register any brain to the atlas. So basically, if you have your own brain, you need to define the anterior commissure, the posterior commissure, and then the Telaera space, and then you have these different boxes in Telaera space. So this box, this box, this box, this box. And then essentially you need to stretch each part a little bit in there to make it align with the Telaera brain. Now this was, of course, before computers. Once computers became available, you could, of course, do the stretching. I actually don't know how they did the stretching with the anatomical sections. Maybe they actually put them, I don't know. Not with, of course, the original Telaera, but with your own. But once you had imaging, you could, of course, normalize the data that you have, the MRI data, by stretching or sharing it into the size of the Telaera space sub boxes. And this you can essentially do based on templates. So you need a T1 image, and then you have your own image of a participant, and then you somehow need to morph your own image into this. And if you morph all of your own images based on your participants into the one that is MNI based, then of course all of them are kind of normalized the same way, because they are all normalized with respect to a specific image. So these MRI-based templates, they are, and this is how this whole thing is related. What happened there is people acquired 300, for example, for this MNI 305 template. People at the MNI, so the Montreal Neurological Institute, acquired 305 T1 images, and they were aligned to the Telaera atlas using landmark-based registration. So for each of these images, the images were morphed so that they align with the Telaera image. And then these T1 images, these aligned T1 images, they were averaged and then created this MNI 305 template. So MNI space and Telaera space are actually the same thing, because the MNI space things were generated by aligning these 351 images to the Telaera image. And there's another template, the ICBM 152 template, which is a higher resolution than the MNI 355. So this shows actually the images. So this is the MNI 305 image that was created by these people, and now what we can do is we have our own T1 image from our participants, and we can use an algorithm to morph, to estimate the parameters of our participants to align with this image, and then apply these parameters to the data and hence resample it in such a way that it looks like that. That doesn't work anymore with only translation and rotation, of course, because you might have to also inflate or compress a certain brain so that it has the same size as this. So this is the SPM way of looking at the MNI 305, and this is the ICBM 152. There are more templates used in SPM. For example, what I prefer to do is actually directly align the EPI data to an EPI template instead of aligning T1 data to T1 template and then using a co-registration of EPI data and T1 to also get the EPI data into MNI space. One can do that directly using, for example, this SPM8 EPI template. How they were generated, like I just told you the story about these other ones, you can read here. That's interesting, and you learn something. I don't remember how, what's the story behind them, but essentially they are based on some EPI scans that they did and aligned to T1 images and so on, and in the end they had this EPI template. So what a lot of people do, as I briefly hinted at, is, this is what I'm looking for, is to actually use the T1 templates and T1 data from participants and align those, so basically to get the parameters to morph the participant-specific anatomy into the template. At the same time, they co-register the structural data, so the T1 data, and the EPI data. So they try to align the EPI data, which of course always looks a little bit crappy, with the T1 data. And then use the parameters of the T1 normalization with the EPI normalization. And then people do all sorts of things. So, and this is what is shown here. So what one can do, and what is called here one-step normalization, is you have an anatomical image, you align that with a T1 template, and you have morphed your specific participants' data into an MNI-spaced brain. And this is just simple and done. However, of course, this doesn't help you for fMRI data analysis because this is T1 data. If you want to do if you want to have all your fMRI data in one common space, you can take each participant's functional data and align it with the with the EPI template, which is in MNI space. And then you have put all of your functional data into EPI space. That's fine. That's how I do it most of the time. What you also can do, and this is what I briefly mentioned previously, is to align your functional data with your anatomical data on a single participant basis, morph your anatomical data into the anatomical T1 MNI space. The reasoning here is that there's more information in the anatomical data, so that this morphing here is done better if you do it based on the T1 anatomical data rather than on the EPI data. And then use the parameters that you estimate here, use these parameters to go from here to here to do the normalization of the functional data into MNI space. And you can even make it more complicated by, for example, so I think this is a T2 scan. So you can align your T2 scan with your T1 scan, have the T1 scan normalized to MNI space, and align your functional data with your T2 scan, and then take the parameters that go from here to here to here directly on the functional data and have your normalization based on this. So you can do all sorts of things, and I personally prefer this here, this functional. You have your functional data, you morph it into the MNI space by aligning it with the EPI template, and you're done. But I think I'm a little bit alone with that, so I think a lot of people prefer these more complex ways, although there is not really that much data that shows that this is really that much better. So there has been a paper recently which was about what? Was going a little bit in my direction, but then not quite. I think there was some, what was that, only anatomical data, whatever, I don't remember. So the thing is, there are these ways, and you can get completely lost in like using the parameters from this here and there, and of course makes the whole programming more complex. Sometimes I feel people just do it because it can be done, not because there's good reasons to do that. But the basic idea is that you morph an individual's brain into a standard space.
But doesn't the data get kind of like
distorted?
Inaccurate?
Yes.
The more stuff we do, the more of it?
Yeah. I mean, in the end, you just apply one transformation here. But definitely what it means is that the individual raw data is somehow morphed into something different. That's always the case, whether you do it simply in one step or in 3 steps. And this then always means that what you have on the group level representing your single participant is not really what the single participant is really like. So this normalization is never perfect in any sense, because in the end, and this is then where people start being interested in inter-individual differences, no 2 brains are alike. So you can force them to be alike, but then what you get is something that is interpolated and made up, or you cannot do it. The question is, do you want to make statements in your research about humans or about Aline? I mean, you also saw that last week from this classification based on resting state in male versus female, which, yeah, one can do. I don't really know what the point of doing something like that is, but this is then the question, it goes into the same direction. It's like, if you do this for males and females, put them into the same state, but are male and female brains different? And then you can start a whole debate and get very emotional, or you not get very emotional, or whatever. The whole thing is kind of, one can computationally do things. The question still is that reasonable? Does one want to do that? Do we want to find, do different people actually have the same brain areas so that it makes sense? Or does everybody have their own brain? And you cannot really compare different brain areas. But this is how usually things are done in fMRI research for group studies. And that's called anatomical normalization based on MNI templates. So that was everything I wanted to say about preprocessing. Now if you go into a lab, you can either do a year of preprocessing your data different ways, or, and this is what I would advise, is you do one preprocessing screen, you make sure that everything runs, and you use the defaults. That takes you, when you do it for the first time, maybe 2 or 3 weeks to have that implemented. So, and then you have the preprocessing, and then you can do actually the data analysis in terms of the statistical modeling. And then at one point you have figured out what kind of data analysis you actually want to do. And then you can maybe go back to your preprocessing. Of course, you want to do everything in script so that you don't do things manually again, and maybe change a little bit with the preprocessing and see how strongly the preprocessing affects your final result. Never do something like you do one preprocessing get one result, and then you start fiddling with the pre-processing, and then you start fiddling with the statistical analysis. This often happens, and it delays everything, and it gets all the fun out of things. So look at pre-processing in a very pragmatic way. If you do the pre-processing differently, your final results will be different because you do a different analysis. So the important thing is that you do everything script-based so that it can be really be tracked, and that you, once you somehow think you have found your result of your study, that you, in a way, protect it a little bit in the sense that if you change the pre-processing a little bit, that not everything goes away, so that your highly sought after statistical significant result, once you make the smoothing 0.5 millimeter less, goes away, and it was really just all, not all, but it was strongly determined by your specific pre-processing routine. But what I want to say, and this is also why I go over pre-processing quite quickly, I could also do a full course on computational anatomy. It's for the interpretation of fMRI studies. The pre-processing is not that important. The interpretation is completely determined by the statistical analysis that you do, whether you do a GLM analysis, a DCM analysis, maybe an MDPI analysis. This really affects the scientific meaning of your study. So if you do a little bit realignment more, a little bit realigning less, that doesn't change the claim and the story that you make about the brain afterwards. So this was pre-processing. Please look at it pragmatically, but this will depend on which lab you work in. So the big thing that is then left actually for to do is to talk about actually the data analysis. And as I said, we will go from now on, we will talk about this, because this is still the workhorse of fMRI, and also for things like computational fMRI plays an important role, and for just understanding statistics. In the summer term, we will talk about this. This you can forget, because that's old school, 90s, nobody's interested in that. This is not as great as it seems, and I will talk about it in a year. Yeah. So this actually then ends the first half of the fMRI course. The next half of the fMRI course is to go back to section 2 and really do section 2 now. And really do imaging. So from next week on, we will talk about, again, so that you know what we are talking about from next week on again, we will talk specifically, for example, about things like that. Yeah? So, but we will start with talking about what differential equations actually are. Good. Questions, pre-processing, anything? No? Good. Then let's stop here and see you next week with whole new courses, GLM and MRI.